Students, actually, Assalamu alaikum. Today we will study about electric fields in material space. This is chapter 5 of the textbook. Okay. So first we will study about current. There are two types of current. The first type of current, okay, the current and the current density is related by the equation I equal to integral over a surface J dot ds. For example, if you have a filament like this, right? This is a filament, and this particular filament is having a cross-sectional area this is having a cross-sectional area S, and an elemental area in this is given by delta S, right? So you can find out this derivative easily, where J is current density. You can say J is current density. So actually there are two types of current. The first type of current is called a convection current. Okay. Case A is convection current. Okay. The first type of current. This convection current is due to the concentration of electrons in a material, right? It is due to a concentration of electrons in a material. So it is basically because of something called a charge density. Okay. So concentration of charges in some material, because of that you have a convection of those charges, and it is not due to it is not because of an electric field. Because of electric field you have another current which is called the conduction current. Okay. So the convection current, you can write the convection current density due to convection current is given by J equal to, it's a vector, is given by rho V, that is the current charge density. This is a charge density into velocity. Okay. Velocity. Velocity is also a vector. It may be in the x direction, y direction, z direction, whatever it is. So here the J is the convection current density. Okay. The J in this case is convection current density. Understand? You can say it is convection current density. Similarly, you have another current called a conduction current. The conduction current is because of an electric field, right? So the current density due to conduction current is given by sigma E. Okay. So you have sigma is conductivity of a material. Conductivity of material, and E is the electric field, right? E is the electric field. So these are the two types of current that you have: convection current and conduction current. Convection current is due to a charge density, and conduction current is due to conductivity and electric field, right? So now we study what is a conductor. You see, a conductor is a material with a perfect conductor. You can say sigma equal to infinity. Conductivity is infinity for perfect conductor. For a perfect conductor you have conductivity sigma equal to infinity, right? So if you have a conductor, the electric field inside a conductor E equal to 0, rho V equal to 0. Okay. For example, if you have a conductor like this, okay, Suppose if you have a conductor like this, you have 2 points. Suppose if the electric field inside is like this, E will be 0. Charge density also will be 0. If you take any 2 points here, A and B, the potential difference between the points A and B, that is given by VAB, equal to 0, because electric field is 0. Understand? So these are the conditions for a perfect conductor. Sigma conductivity is infinity, electric field is 0, charge density is 0, and the potential difference between any 2 points is 0. Right? Normally, the perfect conductor is an ideal case. Understand? Perfect conductor is an ideal case. In general, what you have is some material which conducts, but the conductivity is not infinity, right? So in that case, you can think about the electric field E equal to V by L, where L is the length. Okay. For example, if you are applying a voltage V here, right, and this is the length L, okay, then you can think about E equal to V by L, okay, and if this conductor is having a cross-sectional area of S, you know J equal to, suppose if the current is I, and this is having a cross-sectional area S, right? Now you can write J equal to I by S, right? And you can write for the conductor J I by S equal to sigma I, right? Sigma E, okay, that equal to sigma V by L, right? So from this you can derive the equation for R. As you know, R equal to V by I, okay, that will be given as L by sigma S. That is how you derive the law for the resistance. Resistance R equal to the length of the conductor divided by conductivity multiplied by the area of cross section. This is an important rule that we use. Okay, so you can, if sigma is conductivity, right, sigma is conductivity, 1 by sigma is called resistivity. Okay, 1 by sigma is called resistivity. Right. Now, what we do is we will do a small problem example. Okay, we have a wire of diameter 1 millimeter, okay, 1 millimeter. Conductivity is given by 5 into 10 raised to 7 Siemens per meter. That's the unit for conductivity, right? Has, okay, 10 raised to 29 electrons per meter cube. That's the electron density when an electric field of 10 millivolts per meter is applied. Okay, so first you are asked to find out certain parameters. First we will find out what is the charge density of electrons. Okay. You see, you are given the electron density, number of electrons per meter cube. So the charge density, you can write it as, you can write the charge density as rho V is equal to number of electrons per meter cube. That is the electron density into charge of an electron. Understand? So that will be 10 raised to 29 into charge of an electron is minus 1.6 into 10 raised to minus 19 coulombs. Right? That you have to study. Okay. So you will get the charge density as minus 1.6 into 10 raised to 10 coulombs per meter cube as a charge density. Understand? The second, you are asked to find out the current density. What is current density? Current density is J, right? J. J in a conductor, the wire is a conductor, right? Is given by sigma E. You are given sigma as well as E. So you can write it as 5 into 10 raised to 7, which is the conductivity, right? Into 10 into 10 raised to minus 3, right? So it will be coming around 500, that is 500 kilo amperes per meter square, because current density is across an area cross section, right? And the third part is current in the wire. What is the current in the wire? Current in the wire is given by I, right? What is I? I is current density into area cross section, right? So you can write it as 5 into 10 raised to 5, right? Area cross section is pi r square, right? Area cross section is pi r square. We are given the diameter, so it will be pi into d square by 4. Diameter is given as d is 1 millimeter, equal to 1 into 10 raised to minus 3 meter, right? So if you substitute these values, you will get a current as 0.393 amperes. That's how you will find out the current. And fourth, you are asked to find out the drift velocity, because we are applying an electric field, right? So because of the electric field, electrons will be moving with the velocity. That's called the drift velocity. Okay. Now, you see you have J equal to rho V charge density into drift velocity U, right? So you can write the drift velocity U equal to J by rho V, right? So that is 5 into 10 raised to 5 divided by 1.6 into 10 raised to 10 equal to 3.125 into 10 raised to minus 5 meters per second. That's the answer for the drift velocity U. Okay. So that's how you will find out the various parameters in the case of a what we can say a conductor. And now we will do another example. One more example we will do. That's to find out the resistance, right? Suppose if you have a bar with cross section like this. You have a bar with cross section like this. Okay? It has a hole bored along its length. So the length of the bar maybe, this is the length of the bar is 4 meters. Okay. And this question is a lead bar, lead with sigma conductivity is 5 into 10 raised to 6 Siemens per meter. 5 into 10 raised to 6 Siemens per meter bar of square cross section. It's a square cross section. It has a hole, bored along its length of 4 meter. The length of the bar is 4 meter. Okay. The dimensions are given like this. The diameter of the hole is given as how many centimeters? 1 centimeter, right? It is given as 1 centimeter, and one side of the square lead bar cross section is given as 3 centimeter, right? So you are supposed to find out the resistance. Find the resistance, okay, of the bar. That's what you are supposed to find out. So the answer comes like this. You see, first we will write the equation for the resistance, right? Answer is like this. What is the equation for the resistance? R equal to L by sigma S, right? You know L equal to 4 meter, sigma equal to 5 into 10 raised to 6 Siemens per meter, right? Now we are supposed to find out S, right? We have to find out S, right? So you see, this is the cross section, right? This is actually 3 centimeter, right? And you have a hole inside with a diameter that is 1 centimeter. So to find out S, you have to calculate the area of the square, and from that you have to subtract the area of the circle, right? Area of square minus area of circle, right? Isn't it? Area of square is, that is 3 centimeter, that is 3 into 10 raised to minus 2 into 3 into 10 raised to minus 2, isn't it? That's the area of the square, right? Minus, you have pi d square by 4, right? Pi, or else you can write as pi into 0.5 into 10 raised to minus 2 into 0.5 into 10 raised to minus 2. Okay, that's the area. So that area you can calculate, understand? So it may come around 9 minus pi by 4, okay, into 10 raised to minus 4 meter square, right? So if you substitute all these things into the equation for R, you will get it as 974 micro ohms. That's the answer you get for this particular problem, right? That's how you find out the resistance of the thing. Now, I think we will stop this for today's class.